Okay, so good afternoon, everyone.
Good afternoon, sir.
Okay, so uh, before we start, do you have any question? Anyone? Okay.
Sir, yesterday we had some network issue.
Uh-huh.
Can you just give an impression of the proceedings of yesterday in a brief, 2 minutes? Sir.
Sorry, again, can you repeat?
Yesterday we had network issue,
Uh-huh.
so
Okay.
we could not I could not attend much of the program. So could you kindly just give a glimpse of the yesterday program?
Okay. So yesterday we basically focused on the magnetostatics part, where we discussed how a magnetic field can be measured due to how the magnetic field arises due to a flow of current. So this is due to basically we discussed the Biot-Savart law, so which tells you if you
Hmm.
have a, a current wire which carries a steady current,
Okay.
then how the magnetic field will be produced at some point P, so which will be followed by the Biot-Savart law. And then, so this is one way to calculate the magnetic field due to this current carrying wire. So another way
Yes.
is you use something known as the Ampere's law, which is basically you take the line integral of the magnetic field to calculate what is the magnetic field produced due to a current that is enclosed by a loop, which
Okay.
in this case it is similar to a Gauss's law in electrostatic. So this is known as Ampere's law, which is again this is related to, or let me just write down this Ampere's law again. So this is, so if you calculate the line integral of your magnetic field around a closed loop C, which is bounded by any surface, so this is will be equal to the total charge that is enclosed within that surface, which is like bounded by that contour or that line. Okay, so this is depending on the number of wires, for example, or depending on how much total current that is flowing within that Amperian loop. So you can calculate the magnetic field using this formula. So this is the Ampere's law. And then we basically looked at different, so how a material will behave when you are applying a electric or a magnetic field. Okay, so in this case so if I take a charge, so just simply any electric charge, so the force will be the Lorentz force, so which is given by E, sorry, so, so Q into E plus V cross B. So this is the Lorentz force that acts on uh, any charged particle due to electric field and magnetic field B. So now when you look at this force, so this force, particularly for electric field, this is simply the electrostatic case. But in case of a magnetic field, so the charged particle should be in motion. So then only you will have a magnetic force on the charged particle. If there is no motion of the charged particle, so basically there is no uh, force due to the magnetic field. So similarly, and if you want to now find out what is the work done due to this force, so you take a line integral of this F dot dl. So you will find out magnetic force does not do any work. Okay, so the work done due to a magnetic field, the force acting due to a magnetic field is 0. And then we extended this idea like how a material would behave in presence of a magnetic field. So, and when you look at that, so you can divide a material as a diamagnet and a paramagnet
MPH-001 का क्लास भी होगा क्या?
and
MPH-001
ferromagnet. Okay.
Okay.
So this diamagnet, paramagnet, and ferromagnet, so they are like how you distinguish a material based on how when you are applying a magnetic field. So the difference, in a simple way, I can say if I apply a magnetic field B, so there will be an induced magnetization which will be opposite to this applied magnetic field. So these small arrows basically are representing a small magnetic dipole moment which form within the material. So if I take a paramagnet, so I'm applying a magnetic field, so all the moments will be aligned along the field. They will be the same direction as the applied field. And in case of a ferromagnet, so what you have is known as something known as domains. Okay. Of course, these domains are at t equal to 0 when there is no field. But if you apply a field, so these domains start getting aligned, and you will get a uniform and magnetized material. So which is a typical behavior of a ferromagnet. Okay. So the now how do we basically quantify this relation between B and this dipole moment that we are looking at? So these are all due to this origin of this tiny dipole moment. These are due to this atomic dipoles, which are basically are due to your, or let's say we wrote it as M. So instead of mu, so let me write it as M. So M is the origin is basically it is a quantum mechanical in origin, so which is related to the orbital angular momentum and the spin angular momentum of the electron. Okay, so in material, so since we have mostly atoms and or electrons which contribute to this magnetic moment, so this dipole moment that arises in material is due to, so this is, there will be a minus term here, so which tells you that the dipole moment that is induced or that is associated with any atom is related to its total angular momentum L and total spin angular momentum, orbital angular momentum, spin angular momentum, which is quantum mechanical in origin. Okay, so also what we looked at is a relation. So one can also get a relation between B and since we are talking about a collection of these dipole moments, and this collection of dipole moments, one can quantify something like as a magnetization. Okay, so you can define a quantity M, which is your total total dipole moment. So if there are n number of dipoles, so this is n into m divided by the volume. Okay, so this is basically your magnetization, and this quantifies basically which normally you can measure in experiment, and there is a relation between this B and M. Okay, and how they are related. So B is so we are talking mostly again of linear materials. So it is related to B to this quantity H. Okay, so this H, which was which is known as a magnetic induction. So this is known as magnetic induction, which when you look at it, the origin, it is actually due to this H field is produced. H is due to any free current that exists. Okay, so if I take any wire and there is a current passing through it, so current I, so it will lead to a magnetic induction that is correspond to this value H. But that same material or the wire through which current is passing through can also have some magnetization. Okay, so which can also and therefore this magnetic field B that is produced can have the effect from the current, the free current that we are talking about, and this magnetization that arises, which we normally assign it to something known as a bound current. Okay, of course, there is no such bound current really exists, but we can say these small dipole moment that we have in the atoms is similar to you have a nucleus and there is an electron orbiting around it. So we can say we have some kind of electric current that is there due to this orbiting electrons, and which you can assume or say this is something like a bound current to the material. Okay, so that gives rise to your magnetization, and the free current, if there is any wire that is, because you just connect it to a battery, so you have a flow of current, that will give rise to H, and both will contribute to your total magnetic field B, and they will be related in this relation. And in fact, this relation is different for diamagnet, for paramagnet, and for ferromagnet, and on that basis, you can actually distinguish between this material. So if I plot B as so B and let me plot instead of B. So okay, you can plot B and H, for example. So this is my applied field H, which is due to this current carrying wire, and this is the magnetic field that is produced due to this H. So in case of a paramagnet, so it will be a linear. So this is the paramagnet. But as we saw, in case of a diamagnet, so the magnetization will be, so this will be still linear, but it will be very small. Okay, so there will be a very small magnetic field B that is induced due to a magnetic field H, that is a diamagnet. But if I take a ferromagnet, so what I will have is a hysteresis loop. So this is my P and H. What you get is a hysteresis, which is basically tells you that this ferromagnetic material they're completely different in presence of a magnetic field. So typical example, like you take iron or nickel or cobalt, which are common examples of ferromagnetic materials. So this is due to that. Okay, so the next thing which we will, so far what we have discussed is about electrostatic and magnetostatic. So the next thing which we will now go into what is known as the dynamics. So the first experiment that was done or demonstrated this dynamic effect was this Faraday's experiment. This is which is known as Faraday's laws of induction. So what basically the experiment is, so if I take a a current, or sorry, any loop, a conducting loop, okay, and I put a galvanometer or any ammeter, let's say, so which can measure if there is a current through the loop or not. And what he did basically, he changed the magnetic field. Okay, so he brought it closer to this loop and then take it away from the loop. So by changing the magnetic field, so he could see there is an induced current. Okay, so this induced current is actually proportional to how fast or slow you are moving this magnet. So irrespective of whether you are moving the magnet close to the loop or you are moving the loop with respect to, you fix the magnet and move the loop, or you move them both together, so it doesn't matter. So there should be a relative motion of one of this component, either the loop or the magnet, or you can also vary, you can use an electromagnet and then you can vary the magnetic field. So all these situations will produce an induced current. And this was the first experiment which demonstrated that there is something known as a dynamic effect of this electric and magnetic field. Now, this how much current is induced, okay, or this also you can measure it in terms of a EMF, okay, so which you can also measure as a induced EMF. This is the electromotive force, which you can quantify as this EMF. So it's always be proportional to the electric field. So the line integral of electric field in a closed loop or a closed contour. But as we have known, or we know earlier, that for electrostatic case, if I have only a charge distribution, this E dot dl will be 0, okay, in a closed loop. But in this case, it is not 0. Why? Because this electric field that is produced is due to this changing magnetic field P. So there is a magnetic field that is associated with the magnet, which is changing, and that magnetic field is producing an electric field, and that electric field basically drives your current or charged particles, which is a dynamic effect, and that is why also it is known as the induced effect or a EMF or induced current. Now, this induced EMF is, since it is related to the rate of change of the magnetic flux, okay, so this is how Faraday actually quantified his observation. So this electric field is equal to minus d phi by dm. So this is your magnetic flux. And this is a negative sign is there. And we know the magnetic flux that is produced is your B dot ds, okay. So this is the surface integral of your magnetic field. So the magnetic flux, so any flux, when we talk of any flux, that means the flux is like whatever vector field that is passing through a given surface, okay, and therefore, so irrespective of whether it is a flux, a water, you are talking about water, the velocity, or is it the electric field or magnetic field or any vector quantity. So any flux, when we talk about, we write it in terms of this integral form. So this is the dot product of the vector field in the surface defined by this surface S. So any arbitrary surface S. So how much magnetic field that passes through. So here in this case, so if this is my surface, so I say what is the magnetic field that is crossing through this cross-sectional area of the surface. So that is the B dot ds, which is the magnetic flux. So your induced EMF is proportional to or equal to this time rate of change of magnetic flux. Okay. And now if I equate these two relations, so E, this induced EMF is E dot dl. So I can write down the relation that is E dot dl, which is my induced EMF, will be equal to this minus d by dt of this rate of change of flux, and the flux is given by this surface integral B dot ds. And I can take this I can take the derivative, the time, the rate of change of this flux. I can take it inside, so I can write it as del V by del T dot ds. Okay, so this is basically your Faraday's law of induction, so which relates that your electric field, so a electric field is produced due to a changing magnetic field. So there should be a minus sign here. So this is produced due to a magnetic field or the time varying magnetic field. So that is most important here. So this is not a static magnetic field, it is a time varying magnetic field that produces an electric field, which basically drives your charge particles within a loop and creates an induced EMF or induced current in the loop. Now one can write it, this is an integral form. You can also write it in a differential form. So in order to do that, so you have to use Stokes' theorem, which basically relates your line integral to a surface integral. And so the left-hand side, using Stokes' theorem, so I can write down the left-hand side as, so left-hand side will be equal to, so E, sorry, so this is, so curl of E dot ds. Okay, so this is, I'm using a Stokes theorem. So this is about the surface, which is equal to, so minus del B by del T dot ds. And since we are doing it for any arbitrary surface, so we can write as curl of E is equal to minus del B by del T. So this is your second Maxwell's equation, or third Maxwell's equation that we wrote in the beginning, in the first class and also later on in other classes. So this is the curl of E is equal to minus del B by del T, which represents your Faraday's law in a differential form. So which basically means that if I have a changing magnetic field, so that will produce an electric field, and that electric field will lead to a flow of charges or an induced current or an induced EMF in a loop. So this is, you can say this is the first experiment, and then basically when Maxwell put it in this differential form, so this is nothing but your Faraday's law of induction, which which tells you that there is something, a moving magnetic field or a changing magnetic field can produce electric field. Okay, so now let's look at then the question was, so of course this you can actually use, so this induced EMF induced current has a lot of applications. So in fact, when we talk about a generator, electric generator or motors, so that means we are talking of how you can convert electrical energy to mechanical energy or mechanical to electrical energy. So in all those cases, so this Faraday's law of induction is very useful. Okay, applied quite, that is useful in that. So similarly, if you want to measure any any small magnetic field, so this is also basically you use this the Faraday's law of induction to do that. Okay, so this is also is useful when you want to sense the magnetic field. So whether it is Earth's magnetic field or any magnetic field that is produced anywhere. So if you want to use a magnetic sensor, so this is typically works on this Faraday's law of induction. So there are many applications of that. Okay, so now we will look at the third or the fourth equation that we about the magnetic field that we looked at. So that is, we said in case of a magnetostatic field, so curl of B will be simply equal to mu naught J. Okay, so what is J here? J is the current density. Okay, so this is still, let's say, different from the Maxwell's equation that we wrote. So just to summarize the Maxwell's equation, so we always write this as del dot E equal to rho by epsilon naught, and del dot B is equal to 0. Del cross E, what we saw just now, this is del B by del T. Then curl of B is mu naught J plus mu naught epsilon naught del E by del T. So now the question arises, why we need to add, or Maxwell had to add this term so that you can say this Maxwell's equations are complete. So why do we need this extra term? So we know from Ampere's law, this curl of B will be equal to mu naught J. But why do we need this? So intuitively you can think already that since in Faraday's case, a changing magnetic flux or a changing magnetic field produces an electric field. Okay, so similarly, is the opposite, is it possible? That means a changing electric field, can it produce a magnetic field also? Oh, that is, you can say, okay, it should be possible. And this is due to something the term that normally we will use to say this is that it should be symmetric. Okay, so if a changing magnetic field is producing an electric field, so due to symmetry, a changing electric field should also produce a magnetic field. Okay, that is intuitively you can say that. But now, how do we actually know why do we need this extra term that was introduced by Maxwell? So that was, I think, one of the biggest contribution of Maxwell, and that's why this was known as Maxwell's equation. Although, if you look at the individual equations, they are just all come from some electrostatics and magnetostatics or electrodynamics. So we are not calling it yet electromagnetism because until Maxwell, no one has shown that a changing electric field can produce a magnetic field. Okay, so how Maxwell did that? So what he did, so there are, so one is the symmetry consideration, as I said. So when you look at a symmetric point of view, you say this the dot product of E is rho by epsilon naught, dot product of B is 0. Then when you look at a curl of E, so there is a time dependence here of magnetic field. So you expect there should be something, a time dependent term also with respect to E should be there. So from a symmetric consideration, it should be there. But then there is also another way of looking at it. So if I take now, I have this equation del dot E. Let's say we start with this. So del dot call of E is minus del B by del T. So if I take a divergence of this, so this is a divergence of this curl of E. So which is, I can write now del dot B, because I'm interchanging, as you can see, I'm interchanging the operator del and this partial derivative del by del T, because they are independent of each other. So del operator is basically, this is del by del X, del by del Y, so which is operates on X, Y, Z, and the T, this is a time derivative. So that's why I can really exchange. So in a quantum mechanical, or also which like they commute, so I can therefore exchange this. And as you know, the right hand side is 0, del dot B is 0. The left hand side is also 0, because if I take a divergence of curl of any vector, that is always 0. So this is 0 is equal to 0. That is fine. Okay, so now let's look at the Ampere's law, because till now Maxwell has not added or done any correction. So let's take this divergence of both sides. So you will have del dot J. Okay, again, since this is a divergence of curl of a vector, so the left hand side has to be 0. But the right hand side is not necessarily 0. Okay, so this is not necessarily 0. Why? Or I see. So this is not 0. So this term is not 0. Why? So we saw this del dot J is equal to your del rho by del T, which is your continuity equation. So which is basically tells you the conservation of charges. And this, if you have any charge density, okay, or any charge distribution, so then the right hand side of this equation is not 0. So only if there is a steady state current, if there is no charge accumulation or no charges are present, so in this case del dot J will be 0. Otherwise, most of the cases this is not 0. So then how we can say this equation is mathematically correct? Okay, that is one thing. So from symmetry point of view also it looks odd. Okay, so now let's what we know that there is a relation between rho and your electric field. So how it is related? So we know del dot E is equal to rho by epsilon naught. So that implies rho is equal to del dot epsilon naught E. Okay, so that means my del dot J, which is a time of del by del T of rho, so I can write it as del dot epsilon naught E. Okay, and I can now again exchange this partial derivatives. So I can say so I am just rearranging everything. Okay, so this is del dot epsilon naught del E by del T. So I can say my so now I can write this. This is del dot J. Yeah, so del by del. So so when you look at this equation, okay, so what we are saying, this is not 0, not necessarily 0. So it will be because of this continuity equation, because of charge conservation. So I have to add some extra term here, let's say x, I have to add, so that I will satisfy, so this term will add up to 0. Okay, so that means if I add this x term, so which will be minus negative of this del dot mu naught del dot j, so that will cancel each other out and it will be 0. So x should be of the form, so this x should be of the form of minus mu naught del dot j. So in this, if this is the case, so if I add x here, so this will be 0. And now what you see here, so we have some kind of expression, similar expression we can get from this here. So if I write now x is equal to minus mu naught epsilon naught del E by del T. Okay, so not minus, but it should be plus, okay, because the minus sign will be inherent there. So it will be x, if I write x, so if I write x is equal to mu naught epsilon naught del E by del T, add the x term here, okay, then mathematically I will make the equation correct, as well as from a symmetric point of view, that also makes sense. So this is what basically Maxwell did. So so in this case, so your curl of B, so if I write it as mu naught J plus mu naught epsilon naught del E by del T, and now I take the divergence of the left hand side and right hand side, so I will get, it will be 0. Okay, so if you now take the divergence, you will see it will be equal to 0. So this is what a contribution of Maxwell is done here. So this clearly indicates that, so this J, that is the correct density that is produced due to your any wire. So you have put a wire which carries a current. Okay, so that will produce a magnetic field B. But I can also produce a magnetic field if I change the electric field. So a time varying electric field will also produce a magnetic field. So that is kind of completes from a symmetric point of view, although it is still not perfectly symmetric. Okay, so the Maxwell's equations are not perfectly symmetric. Why? So I'll explain that. But right now it looks more or less like similar, because if I change, so I can say now a changing magnetic field can produce an electric field, that is Faraday's induction. So similarly, a changing electric field can also produce a magnetic field. Okay, so this is like we can kind of summarize these equations again, so that we, from Gauss's law, we said del dot E is rho by epsilon. From similar consideration, del dot B will be 0. And what it also means that the magnetic field, so the divergence of magnetic field 0 means when I have it, there is no source of magnetic field, isolated source of magnetic field, or there is no isolated magnetic charge that exists. So which basically, in a way, you say there is no magnetic monopole. And then we said the curl of E will be del V by del T, so minus del V by del T, and curl of B is equal to mu naught J plus mu naught epsilon naught del E by del T. So this basically completes this is how a Maxwell's equation gets complete. And when you look at these equations, so these are not some these are not obtained under certain assumptions or any. These are all known as the fundamental laws of nature. Okay, so these four equations are pretty much known as the fundamental laws of nature. So this is basically how the nature behaves. Okay, so if I have charged particles, uh, if I move the charged particle and produce current, so they will produce electric field, a magnetic field, and they will follow this behavior. Okay, this is the fundamental nature of our existence, basically. So that's why Maxwell's equation is kind of considered as one of the most fundamental that tells you about the nature or in a fundamental way. Okay, so you can write these equations also in integral form. That is also important because many a times you will be in order to calculate or find out this electric and magnetic field, you need to perform integration, which
Sir,
is yes.
J is what? J is standing for which term?
J is current density.
Okay, sir. Thank you. Thank you.
So current density means if I have any, so this is just related to, so how it is related to current. So if I want to find out, or I know what is the current, so this is, so density, current density is basically the current, the charges flowing per unit time, per unit area. Okay, or let's say current per unit area. Okay, so that is your current density. So if I know what is the area through which this the current is flowing, so I take integral over this surface, so I'll get the total current to the surface. Okay. So this curl of B when we are writing, so also sometimes you will see this is also one can write as mu naught J plus a JD. Okay, so JD is your epsilon naught del E by del D, which is known as a displacement current. But remember, there is no such physically any displacement current that exists. Okay, this is we are just saying just to so that you can distinguish it from a current density that is the actual current density. So J, that is always the actual current density due to a real flow of current. Okay, so real flow of charges that gives rise to this current density. But JD, that is displacement current, was kind of used in the beginning when Maxwell talked about it. But there is no such displacement current that flows in a wire or in a loop or anywhere. Okay. Uh, okay, so we should also able to write down all these equations in integral form because that is essential when you want to calculate the electric field. So the first, as we said, del dot E is rho by epsilon naught, which you can write as E dot ds over the surface will be the total charge enclosed. So 1 by epsilon naught, total charge enclosed. So del dot B is 0, which is again your B dot ds is always 0. Now, if I write curl of E equal to minus del B by del T, so so in these two cases, you use the divergence theorem to get this, and in the curl case, so you use the Stokes theorem, so which you basically get a line integral over a contour or over a path. So E dot dl will be equal to minus d by dt. So B dot ds. Okay. And okay, so when you look at these two things, so you don't now you can say, okay, here b dot ds is 0, so I should say the time derivative should be always 0, but that is only correct if we are talking about a a constant magnetic field. Okay, so if there is a time varying magnetic field, so this term is not 0. Okay, so the right hand side is not 0. Only if there is a uniform constant or a magnetic field that is produced due to a static or a steady state current. So in that case only this b dot ds will be 0. Otherwise it is not 0, because there will be charges, okay, so which can produce, I mean, due to the changing magnetic field, so they can produce a electric field. Okay, so you have to be careful when you write these equations, and you should know exactly what is the situation in which you want to apply these equations. Okay, so curl of B will be mu naught J plus mu naught epsilon naught del E by del T. So in an integral form, so you will write as B dot dl is equal to mu 0 I enclosed. So this is all the free, that is charge currents that you have, plus mu naught JD. Okay, so where your JT is equal to epsilon naught del by del. So this is how you can write these equations in a differential form and the integral form, and you should know under what conditions or circumstances you should apply these equations. These are all fundamental equations of nature, and you should also be aware of what is the physical meaning of all these equations. Okay, so this is the most important thing that you must know when we talk about Maxwell's equation. Okay, so let's write down this equation for a. So let's say if I have let's say we write it for a situation. So these 4 equations, let's write down it in vacuum, where I have no charges and no electric current, no charges. Okay, so this Maxwell's equation in vacuum, and so where I say it is a charge-free region and electric current-free region. So rho is 0, J is 0. Okay, so everything is 0. So we were talking in vacuum, there is no charges are there, there is no current loop is there, so everything is 0. So how the equation should look like? So very simple. So del dot E will be 0 because rho is 0. So del dot B is anyway 0. Then curl of E is still minus del B by del T. Okay, so because we are not saying B is 0, so we are just simply saying rho is 0 and J is 0, and your curl of B is simply also equal to mu naught epsilon naught del E by del T. Okay, so this is how the Maxwell's equation would look like in vacuum and in a source-free region. So this is also known as a source-free region. Source-free means there is no charges or no charge distribution, no current distribution as such. So if I now take, let's say, the curl of this two equations. So let's say take the first equation. Let's calculate the curl of this. So it is again, I can interchange because these operators are, one is space operator, one is a time derivative. So I can exchange this. So if I write the curl of this equation, so I am taking the curl of this. So you can use a vector identity where the curl of a vector would be the gradient of the del dot E minus del square E, and the right hand side is curl of B, which is simply mu naught epsilon naught del E by del T. Okay, so we know again del dot E will be 0. That is from the first equation we know. So what we are left with is del square E is equal to minus, so minus sign will just cancel out from each side. So there is a minus sign here, there is minus sign here. So del square, or to take the constants outside, so it is simply del square E by del T square. So similarly, if you take the curl of the second equation, so you will get again del square B will be equal to mu naught epsilon naught del square B by del T square. So this equation, if you look carefully, it looks quite similar equations you have come across, particularly what is known as the wave equation. Okay, so a wave equation, which you can write as del square F or del square psi, whatever you want to write, is equal to 1 by V square into del square F by del T square. So on one side, you have a partial derivative, the space derivative, okay, del square, this term is a space derivative. And on the right hand side, you have a derivative which is a time derivative. Okay, so this basically describes a wave which is moving at a velocity v. Okay, so this equation. So that means the velocity of this wave. So if we say, we can say now this electric field and magnetic field actually exist as waves. Okay, and they move with a velocity which is equal to square root of mu naught epsilon. Okay, so this is the velocity. Now, if you substitute these constant terms, so we know what is the permeability, what is the permittivity of vacuum. So you just substitute that, and what you will get is V is equal to C, that is speed of light. So which was very surprising to many, and of course to Maxwell as well, and which immediately tells you that these electric and magnetic field, they can exist without any source. Okay, so they can move as a wave without any charge distribution or any current. So you don't need that. But electric field and magnetic field can exist. They can move like a wave, and they move at a speed which is equal to the speed of light. And that immediately indicated that light that we talk about is nothing but an electromagnetic wave. So until that time, so it was not, people did not know that you can say a light like the sunlight or any light that we are producing, we can call it as a wave, and for that matter as an electromagnetic wave. So this simple derivation, it is, you can say it is a purely mathematical thing that we are talking about, but this indicates that your light is nothing but an electromagnetic wave, whether it is sunlight or UV or X-rays. So all light that which were known at that time or which were discovered later on. So everything was then people realized is a form of electromagnetic wave. So what it means, that means this wave can, so this is a wave, that means it can propagate in free space. And this is not like not like your typical sound wave, or let's say a wave that on a that you create by throwing a stone into a pond, like a water wave, or it is not like any mechanical wave that you can produce by vibrating a string, okay, so moving some string or wires. So nothing like that. It is a very different kind of wave, and this wave is simply due to a propagation of the electric and magnetic field in a special way, and they can propagate in vacuum, okay, so without any medium, without any source, anything, and they can propagate. So this is the kind of a new insight this Maxwell's equation that brought, which is actually very new at that time. Almost no one has thought about. And that's why Maxwell's equation is kind of treated as most fundamental laws, as well as this is one of the most important aspect in physics, this Maxwell's equation. Okay. So this is basically, it tells you that light is an electromagnetic wave, and we can call it a electromagnetism, and this kind of distinguish from earlier notion or earlier people used to think that electricity and magnetism, they are two different things altogether. But Maxwell's equation, and particularly this behavior, showed that electricity and magnetism, they are not really different from each other. They are just the same thing. They are expressing in a different way. So the electric field can produce a magnetic field. A magnetic field can produce an electric field, and both can sustain each other. Both can move, and they can move at a speed, the speed of light. Okay, so this is why we are calling it as electromagnetic theory. So it is a combination of electricity, magnetism, which earlier people used to think they are completely separate. But Maxwell's equation and this consequent understanding led to the realization that electricity and magnetism, they are not different, but they are the same thing, but expressed in a different way. And therefore, we are calling it as electromagnetism together. So this is kind of a unification, first time, where two different physical observations, phenomena, were kind of fundamentally unified. Okay, so this is a unification of electricity and magnetism, that, or electromagnetism. So that's why it is quite important to know in physics. Okay, any question so far?
No, sir.
Okay.
Sir, kindly
Yes.
little explain me hysteresis of ferromagnetisms. The hysteresis, what is the
Hysteresis.
hysteresis? How it is being interpreted? Because
Okay.
please, sir.
Okay. So there are two ways you can actually plot this hysteresis. Okay. So this is in a x-axis, I'm plotting B, and a y-axis H. Sorry, in the x-axis I have H, that is the magnetic induction. So this
What
H
is
is due to, what is it? It is due to the current that is in a, so current in a wire. So if I have any current, okay, and a current flowing through any wire will produce a magnetic induction H. So, and now once you have that, so in a material, so what will happen? There will be a magnetic field, B field, that will be generated there, which is different from your, what is the actual magnetic induction. So what is the difference between that? So as I said, B is equal to mu naught H plus M. So we can write H, this magnetic induction, is equal to B by mu naught minus M. Okay. So which also sometimes people also, you can also write it as B is equal to, so if I think it is like a linear material, okay. So in terms of susceptibility also you can write M is equal to chi into H, okay. So in that case, B is equal to mu naught H plus chi into H. So it is chi here is the magnetic susceptibility. So this will be equal to mu naught 1 plus chi into H, which is equal to your mu into H. Okay. So this 1 plus chi, which is also known as a relative permeability. Okay. So this is the relation between B and H, and which is different for different materials. So for ferromagnet, you get a hysteresis, which means the what is the magnetic induction, what is the magnetic field that is generated due to this applied magnetic induction, or simply nowadays also, I mean, you can call it simply as a magnetic field, external magnetic field. So this is your magnetic induction, or you can simply call it as a external magnetic field. So this external magnetic field produces a magnetic field B, which is different from this H value. And how it is different? So it is different by a factor, this mu naught M. Okay. So this M that is induced, the magnetization that is induced or that exists within the material. So this can exist spontaneously. So there is, you don't have to apply any external field to get a magnetization. So for example, if I have an external field, H is 0, okay. So I still have B, which is non-zero, okay. So which, because at H equal to 0, so B, so at H 0, so B is simply equal to mu naught M. So that means the magnetic field that is generated within the material will be equal to how much magnetization it has. And you still have a magnetization without any external field, which is not the case in any other material. Okay, so that's why ferromagnets are, they have this peculiar hysteresis. Now, also what happens that when I am increasing this external field, so I get a kind of a saturation here. Okay, so this is a positive. I also have a negative saturation. So that means a situation will be there when the material, if it has domains, so it will all magnetize in the same direction. So in at this, so all these domains will disappear and you have only one domain, so to say. That means all the magnetic moments will be pointing in the same direction. So similarly, the same here. So if I am reversing the field, so the magnetization direction will be all in the opposite direction. Okay, so this is the negative saturation, positive saturation. I also have something as a remanence. That means without any external field, so I still have some residual magnetic field that is purely due to the magnetization of the material. That is your remanence. And also what happens here is there is during the reversal process. So how the reversal occurs, that means I have to rotate these dipoles or the magnetic moments and make them opposite. Now in this process, so what happens, I have a situation where I have a magnetization that is 0. So when you look at, so this crosses the x-axis here, so that means the magnetization is 0 here, so which corresponds to your known as the coercivity. So this is again a term that is used. So coercivity shows what is the magnetic field that I need to apply. So I have also a positive one and a negative one. So how much magnetic field is required to reverse this magnetization completely. So I have a completely positive saturation, positive magnetization, and I need this much field so that the magnetization goes to reverses and goes to negative. So similarly, I can do the same thing. So I start from, let's say, this point, and when I'm decreasing the magnetic field, so I will go through the remanence, then there is a reversal, then it goes to negative saturation. Again, if I now decrease the field from negative saturation, so it does not follow this path. Okay, so this is also important. So it is not following this path. So when I am decreasing the field, but rather it goes through another path. Okay, something like this, where I have a positive coercivity and then a positive saturation. So this is this tells you that the ferromagnetic material remembers in which direction the magnetic field was applied. So it will follow a path which is determined by the history. So that is why we are calling it as a hysteresis. So it depends on the history. So whether you are coming from a positive saturation or a negative saturation, so which path the magnetization will follow, it will be decided by the history of that. Okay?
Sir?
Yes.
Sir, so what is exactly H and how it is different from M?
From M. H, I said it is simply a external magnetic field. So if I take, let's say, for example, any electromagnet, okay, or any solenoid you take. So you take, let's say, a piece of like a cylinder, and you just wound a wire, copper wire around it, and then you pass a current through that wire. Now, you this will produce a magnetic field. Okay, so that magnetic field is basically your H. Okay.
Okay, so the magnetic field because of the flow of the current.
Flow of the current, simply the external, any current, that real current, okay, so that will flow through a wire, any loop, any conducting like element, so that will be your H. Now
And
that
M-
H can magnetize the material. Okay, so if I have, let's say, so if I have this H, or okay, so or take like a solenoid. Okay, so I have this kind of wire one around it, and I am passing a current through it. So there is a H due to this current. So H is equal to your so N into, so number of turns into this, the current that is passing through this the current through the wire. Okay, so this is the number of turns of the how many turns you have and the current through it. So that is simply H. But B will be here mu naught H plus if there is any magnetization that is induced due to this magnetic field H. So this external field can also induce a magnetization if there is a material, for example. So if I put a ferromagnetic material, so I can induce a magnetization M here. Okay. So here I will induce a magnetization due to this field, and then this will change the B field, which is the sum of mu naught H plus mu naught M. Okay. And this M is purely a material property. Okay. So what will be the value of M? So it depends on whether it is a paramagnet, ferromagnet, or whatever, what kind of material it is. It can be very huge, it can be small. Okay. So if I say there is no material, okay, so in that case, my B will be simply equal to mu naught H. So there will be basically no difference between B and H except this constant term. They will be the same. They will be in the same direction. Everything will be same. Only they differ by a value. This mu naught H. Otherwise, if there is a material and there is a magnetization, so this B and H will be different. Okay.
Yes, sir.
This is so H, as you can say, H is simply due to the you call as external field, magnetic induction, whatever it is due to simply a current carrying wire that produces H. Okay. Okay, fine.
Okay, sir. It's thank you. Thank you.
So let's then move on. So what we
Sir, what is the unit of H, sir?
sorry,
Unit of H, what is the unit of H?
unit of H. Unit of H is ampere per meter.
Okay, sir, thanks.
It is ampere.
And thank you, sir, for sending this Google class materials. Many thanks.
Okay. Okay. Right. So this is simply ampere per meter, or so it depends on actually the whether you are using a CGS unit or SI unit. So in SI unit, it is simply ampere per meter. But sometimes, if you talk of CGS, people also use Oersted, or people also use Gauss. Okay, so there are different. So Oersted is basically most of the times also used quite often. This is a Oersted field that is in the experiment that Oersted did. So you can use depending on the unit. Okay. And B and H will be, so the unit will be different because you have a mu naught term here. Okay. So the value may be not different, so you have to divide, but the unit will be different because of this mu naught, the permeability. So B is typically expressed in Gauss or Tesla. Okay, so that is the typical unit for B, and H will be in Oersted or in ampere per meter.
Oh.
Okay, so let's come back to our Maxwell's equation. And as we saw, this for Maxwell's equation, when we write it in vacuum, so you can kind of unify now electricity and magnetism, and we call it as a electromagnetism, which represents something known as a electromagnetic wave. Okay. Now the question is what kind of wave it is. So I think you are familiar with this term, so which is known as, so this electromagnetic wave is known as a transverse wave. So which means the propagation direction, so it is always perpendicular to the electric and magnetic field. So your propagation direction is perpendicular to your electric field and B field both. And also the electric field and B field, they were also mutually perpendicular to each other. Okay, so this is the interesting aspect of electromagnetic field. So you will see some if you type electromagnetic wave, so you will always see this electric field vector in one direction, magnetic field in one direction. They are mutually perpendicular to each other, and they are also perpendicular to the propagation direction. So if the wave is propagating, let's say, in a z direction, or let's say y direction, so electric field, if it is in a YZ plane, then the magnetic field will be in the XY plane. Okay, so something like that. They will be always perpendicular to each other. So in the book, you will find some problems and like how you can write these wave equations and solve these. So you can calculate the divergence curl of these things. And one thing which is also I should tell you here. So you can write down any wave equation. So we wrote the wave equation like here. Okay. So del square E is equal to mu naught epsilon naught del square E by del T square, or del square B mu naught epsilon naught del square B by del T square. So we write a wave equation, and let's say you will find a solution. So there can be several solutions for this electric field or magnetic field. Okay. So because it is a mathematical equation, so you can have several solutions to this equation. Okay. So, but all solutions do not represent an electric or a magnetic field. So this is very important. So which solutions will correspond to your electric and magnetic field? So those solutions which satisfy this Maxwell's equation, so they only will represent the electric and magnetic field. Okay, so this is, you be careful about this, because many a times you will see, so I'm solving for this wave equation. Okay, so in this case, I mean, I'm writing it E, but it can be anything, any function. Okay, so it can be any function. So now I find a solution. So for this electric field, for this function, and I write down that function. But whether that solution, whether it is an electric field or not, it will be decided. So to say whether this is an electric field or not, so you have to find out, or you should see whether del dot E is equal to 0 and curl of E is equal to minus del B by del T. So that means this, so it depends on the situation. So in this case, okay, I'm saying del dot E because we're talking about the vacuum. But they have to satisfy the Maxwell's equation. So Maxwell's equation basically puts a constraint or tells you which solution of this wave equation will represent an electromagnetic wave. Okay, so therefore you have to be careful when you are solving this wave equation, and any solution will not always represent. It may satisfy this wave equation, but they may not be represent a electromagnetic field. Okay, so in order to say that they are electromagnetic field, so they have to satisfy the Maxwell's equation. Okay, so this is important. Okay. So now this electromagnetic field, so since we are talking about this electromagnetic field as a wave, but this wave is actually a real wave, a physical wave, right? So physical wave means it is associated with this, like what we are talking about, this electric and magnetic field. They are real, and they also carry energy and momentum. Okay, so like a wave, so they will carry also energy as well as momentum. So this is also important because that is how, like when we talk light that travels from sun to us, so it carries energy. Definitely, it has energy. Okay. So momentum, of course, we cannot really feel it, but we know that this electric and magnetic field can uh, uh, can impact a force, or can you can apply a force on any charged particle due to this electric and magnetic field, and that's why we know this force is always the rate of change of momentum, and that's why if they are giving some part of momentum to this, so if a charged particle is at rest and the electric field gives a force to that, so that means it is giving some part of its momentum. So the wave, that means, also carries momentum as well. So this EM wave has energy and momentum. Now, what is the energy associated with electric field and magnetic field? So this is again simply we just do it from the classical electricity and magnetism. It will be exactly the same for any electrostatic or magnetostatic case, which is the energy associated with electric field is so half epsilon naught E square dV. So here dV is basically, so we have to integrate over the volume, over the space where this electromagnetic wave exists. So similarly, the energy associated with a magnetic field is 1 by 2 mu naught V square dV, so over this volume. So that means if I want to calculate the energy in the entire space, so I have to integrate over the entire space. So this is this is again taken from your electrostatic and magnetostatic state. So if whether the electric field is due to a charge distribution, or that exists in free space, electromagnetic wave, does not matter, but the energy they will carry will be exactly the same. So depending on this magnitude of this E square and so on. So they will also so one thing which is normally when we talk particularly of electromagnetic wave, so we represent this energy, or we say something about the energy density. Okay, so this energy density we define, which is as the energy per unit volume, and this so we represent this energy density. So rather, so we define something known as a Poynting vector. Okay, so which is your cross product of E cross P. So this is a Poynting vector that is associated with the electromagnetic wave. So simply you have to take the cross product of electric field and magnetic field. And the conservation of energy can be written as, so del U by del T. So this is the total energy density that we are talking about. Energy density means energy per unit volume is equal, plus del dot P will be equal to 0. So this is the conservation of energy term. So like we wrote for conservation of charge, like del dot J plus del rho by del T equal to 0. So similar expression is here. So this is the rate of change of the energy, the total energy of your electromagnetic wave will be equal to this divergence of this Poynting vector P, which is defined here. Okay, so this is normally how one can use and find out how much energy is being carried by your electromagnetic wave. Similarly, the momentum also, so it carries certain momentum, as I said, because the electromagnetic field can give or accelerate some charges or decelerate some charges. So it can give some forces, and that is related to rate of change of momentum, which can also be quantified. So this is about the electromagnetic wave. Is one thing which we would need moving forward. Like so far, we are talking this Maxwell's equation electromagnetic wave in terms of the electric and magnetic field. But in case of magnetostatics and electrostatics, or at least in electrostatics and part of magnetostatics, we introduced a concept known as a scalar potential and vector potential. So the question is, how do they fit into this electromagnetic theory and Maxwell's equation? So do they have any relevance here? So this is, so when you look at a potential, okay, so the potential, whether it is the scalar or vector potential. So this definition of this potential is depends on a reference point. Okay, so we said if I am defining, so if I take an object, okay, and this is, it is at a height h, okay, so I can say this potential energy is mgh. So this is the mass of the object. So this is simply I am measuring with respect to this reference point, the Earth's surface. So I can change this reference point and this potential energy. I just have to add a constant term to that. If I change the reference point from here to here, so I can just add this constant term, which is basically tells you what is the potential energy of this surface with respect to this reference point, and then I will get what is the potential energy of this object with respect to this reference point. So this is simply how you define the reference point. So that will decide what is the potential, scalar potential. And that means it is a, what we call is something known as there is a gauge freedom. Okay, so this is known as gauge freedom. So there was, I think, one question yesterday regarding this Coulomb gauge. So we will come to that. So this is what we call as a gauge freedom. So now if I am doing a gauge transformation or moving from one reference point to another reference point, I just have to add any constant, some constant, and then I will find out what is the potential energy without really affecting the overall description of the material itself. So without saying without changing the position or without changing the momentum or the mass, I don't have to change anything of this object. I can just do a transformation from one reference point to another reference point and add a constant term, and I get a potential energy of this system. So similar thing is also we can do in electric and magnetic field. So electric and magnetic field that we are talking about, these are all real physical things. Okay, so they really exist. Now the question is, but we can write the electric field as a gradient of a scalar potential V. Now the question is, if I do a transformation, I expect this electric field, which defines the reality, it should not change. Okay, so which is actually correct. So like if I take V plus some constant, so electric field, that is gradient of V plus a constant, this will be still the same, minus gradient of V. So even if I change any reference point, how I am defining the scalar potential, so scalar potential which is not representing my actual or reality, the physical reality, that I can change, I can transform. And but still the electric field is not going to be affected due to that transformation. So this is known as something known as a gauge invariance. So what it means that the real physical things, which in this case the electric and magnetic field, so they should remain invariant. Okay, so they should not change. When I am changing the underlying parameters, which I can probably use to describe this physical reality. So I can use a vector potential or a scalar potential to describe electric and magnetic field B. But if I am transforming those scalar potential or vector potential, I can do a transformation. I can which we call as a gauge transformation. Okay, so I can do a gauge transformation of my V and this vector potential A, but still this is not going to change the reality, that is the electric field and magnetic field, which actually we encounter or we experience. So this is something which is interesting in electromagnetism. So let's look at that, how we can find or define this potential and vector potential. So this is so far what we know it is for electrostatic and magnetostatic case. So here is gradient of V, so B is curl of A. So this is only for magnetostatic and electrostatic case. But what happens when this electric field and magnetic field is varying? Because so for electromagnetism, we saw that the electric field, a time varying electric field can produce magnetic field, and a time varying magnetic field can produce electric field. So what it means, so when we say there is a time varying electric field and magnetic field, so how that affects the variation in potential and the scalar potential and vector potential. Okay, so and this also here what we are saying, this gauge invariance tells that the electric field and V, the magnetic field, remain symmetric, or whatever symmetry they follow, they remain unchanged. Even if you are doing a time change of that, So the scalar potential or vector potential that we are assigning or we are using to describe it, so they will transform in such a way that these E and B field remains invariant due to these changes. So let's look at those aspects. So if I, again, we will start from Maxwell's equation and try to write down. So the aim is whether we can write down a Maxwell's equation in terms of these potentials, okay, scalar and vector potential. So we start with, again, a simple case. So we say, let's say del dot B is equal to 0. And we say, so curl of E is minus del B by del T. So these two equations in Maxwell's equation are inherently free of any charge or any current. Okay, so if you look at these two equations, so there is no charge here involved, so no magnetic monopole or magnetic charge. So magnetic charge is 0. And here, similarly, you can say the electric field, there is no current, that is also equal to 0. This is the external current we are saying. So what we are saying that if I have a wire, okay, a current is flowing through that, so that wire is not going to produce an electric field. Only if I change the magnetic field nearby that wire, or somehow I change the current through the wire as a function of time, so then only I can produce an electric field. So basically, the current and magnetic charge are 0 here. So this is what we call as a source-free equations, kind of that. And we will use some vector identity now so that we can write our Maxwell's equation or express Maxwell's equation in terms of this vector and scalar potential. We know that, of course, we know that B is the curl of A. Okay. Why we could do it? Because we know that we can write a vector as a curl of any vector. So always the divergence of curl will always be 0. So that's why we are able to define B as curl of A, because of this equation only. And now let's look at the curl of E, this equation. So we know that B is equal to curl of A. So let's find out what is curl of E. So now this will be minus del by del T into curl of A. Okay. So so this is minus. Okay. So I can now interchange. I can interchange the time derivative and the space derivative. So I can write down now curl of E is equal to curl of minus del A by del T. Okay. And I can so write down E plus del A by del T equal to 0. So I'm just taking it to everything to the right hand side. Okay, so this is curl should be there. Okay, so this is fine. But we also know that if I take a curl of a gradient of any scalar function, so psi is a scalar, and I'm taking the gradient of it, and the curl of a gradient is always 0. That is for true as a vector identity. Okay, so this is curl of graph of any scalar function, graph of any will be always 0. This is a vector identity. So that means I can express this term here. So I have a vector term here. So this is, I am using a curl of some vector. So I can write this term as a gradient of some other scalar function. Okay. So what I am just doing is using this identity, and I am saying I can write this vector as a gradient of some scalar function, psi or phi, whatever you want to write down. And I will write a minus sign here. So which is useful, we will see later. Okay, so I can write it like something like this, a gradient of a scalar. So the electric field, now I can define as gradient of the scalar minus del A by del T. So now what you see clearly, which is pretty interesting right now. Look, so we have an electric field which we are defining as a gradient of a scalar and the time, so rate of change of the vector potential, a vector A. So this, the first term is, again, you can say just simply this is the potential, the scalar potential that we discussed. Okay, so this is clearly represents, this is the scalar potential, which is that comes from your electrostatic case. But in electromagnetism, where we talk about time varying field, so in that case, electric field will be represented by the scalar potential, of course, the electrostatic one. But in addition to that, it also depends on this time rate of change or this rate of change of the vector potential. So the electric field is not only, it does not depend only on the scalar potential, it also depends on the vector potential. This is important. Okay, so this is the straightforward thing, so which is the implication of dynamic that we are talking about. So in case of electrostatic, so if I talk of electrostatic, so E is simply gradient of psi or gradient of phi, whatever you want to write. And in that case, so A, del A by del T will be 0. So in case of electrostatic. Okay, so what about the magnetic field? So one can also write down the magnetic field as well. Okay, right, we are describing the electric field. Oh, sorry. So the magnetic field already we have defined in terms of the vector potential. Okay, so this is your curl of A. This is how we have defined. But we don't know whether it should depend on a scalar potential, like the electric field depends on a vector potential, whether the magnetic field should depend on a scalar potential or not. Okay, so so basically, what we could do, like we have two equations. Let's say del dot B is 0, Maxwell's equation. So del dot B is 0, and curl of E is minus del B by del T. And we can write this electric field in a dynamic case as if with a scalar and vector potential. Which is basically, we can say, we are now able to write at least two equations, two Maxwell's equation in terms of this potential, corresponding potentials, scalar and vector potential. So now let's look at the other two equations. Okay, so the other two equations are del dot E is rho by epsilon naught, and curl of B is mu naught J plus mu naught epsilon naught del E by del T. So these two equations are also known as inhomogeneous equations. So other two equations are homogeneous equations. So these are all differential equations we are talking about. Okay, so this is the inhomogeneous differential equation. So now, since we have expression for E in terms of the scalar and vector potential, so let's substitute that in this first equation. So we write E as del dot minus gradient of psi minus del A by del T, which is equal to rho by epsilon naught. Okay, so the first term is simply minus del square psi. So del dot del, so this is a del square psi. And the second term is minus del. So again, I am interchanging the integral, the time derivative and space derivative. So equal to rho by epsilon naught. And or in a, so if I take the minus sign out, so I can write down this as del dot A is equal to minus rho by epsilon naught. So, and so this is one equation that I have obtained by substituting the form of E in terms of its scalar and vector potential. Now, let me write down this curl of B, which is curl of A basically, which is equal to mu naught J plus mu naught epsilon naught del by del T. And I just simply again write gradient of psi minus del A by del T. Okay. So I'm simply writing this E that we have just derived this expression and writing, substituting that in this equation. So in place of B, I'm writing curl of A, and in place of E, I'm writing this. So now again, you use a vector identity. So the first one will be del square A minus there is one term, okay. And del dot A. No, sorry, so this is the other way around. So the vector identity would be, so this is curl del of del dot A, the gradient of del dot A minus del square A will be equal to mu naught J plus, or so simply just writing it exclusively. So it will be minus mu naught epsilon naught gradient of del psi by del T, and minus mu naught epsilon naught del square A by del T square. Okay. And so we do a little bit of rearrangement of everything, and take these the left hand side. So rearrangement, we just do it. If you do that, so what you will get is del square A is equal to del square A minus mu naught epsilon naught del square A by del T square, then minus the gradient will be del dot A plus mu naught epsilon naught del psi by del T equal to minus mu naught J. So we are just rearranging this equation, and if I do that, so you will get something, this expression. So this is basically kind of we are writing a Maxwell's equation. It looks complicated, of course, but this is how the Maxwell's equation can be written in terms of the vector and scalar potential. So we have got rid of all E and B terms. Okay, so that is the idea here. Okay, so once you have done that, so now let's look at the form of A, and what we are saying is these equations should remain unchanged. Okay, so if I am doing a transformation of A, and if I am writing A in other form, or the psi in other form, okay, so if I change a reference point or I do a gauge transformation of psi and A, so I should be still able to get the same E and B, or I should be able to satisfy these Maxwell's equation that I have written for A and the psi. Okay, so for example, if I say you write a vector potential as A plus gradient of another scalar chi, and you do that, so you will get the same B field. So this is a gauge invariance of magnetic field. Okay, so if you take the curl of both the sides, you will get basically the magnetic field B. But how that is going to affect my phi? That is the question. Now, if I am changing the vector potential A prime to A plus some another gradient of another scalar, so I can get the same magnetic field B. But what is about psi? So let's look at this equation where we define, like we said, E is equal to minus psi minus del A by del T. So now what we have done is we have changed A to A prime. So this is now gradient of psi. This is A. So we have done a transformation to A prime. Okay. So this will be equal to del A by del T minus gradient of del chi by del T. Okay. And so if I now combine the scalar terms, so I can write this as psi plus del chi by del T. Minus del A by del T. Okay. So what it shows me that by changing the vector potential by this term, so I also need to change the scalar potential as well. So now new scalar potential I am defining as psi plus del chi by del T. So this changing the vector potential also affects the scalar potential in electrodynamics. Okay, so this is what this exercise tells us. So whenever we are doing a transformation of one of the potential, whether it is a scalar or vector potential, we need to also do a transformation of the other potential as well, so that we retain this gauge invariance of electric and magnetic field B, and then they will satisfy this Maxwell's equation or the Maxwell's equation. They will satisfy that, and we can get the E and B field irrespective of whether the underlying potential is. Okay, so one thing is we can write these Maxwell's equation in terms of scalar and vector potential, and if we want to do a transformation of any of the potential, so the other potential is getting affected because there is a relation between E and B. So in order to keep E and B invariant due to this transformation, so we if one of the potential is affected, the other one is also getting affected. So actually these equations look very complicated, of course, and there are certain conditions which are imposed, which can retain what I just they can retain what I have just said. So retain in the sense they will keep E and B invariant under the transformation of the vector or Coulomb potential under certain conditions. Okay, so those conditions known as one condition is known as a Coulomb gauge, and the other one is the Lorentz gauge. And particularly Lorentz gauge is important because this Lorentz gauge condition led basically Einstein to the special theory of relativity. Okay, so very dissimilar subject on the surface. They would look like, oh, they are very different, electrodynamics and special theory of relativity. But the Lorentz gauge, or this in Lorentz gauge in electrodynamics, is a foundation for the special theory of relativity. Okay, so that is a deeper connection that you have between electrodynamics and special theory of relativity. So we'll look at this Coulomb gauge and Lorentz gauge in the next class, and then we will talk about how these electromagnetic waves uh, actually can be calculated in vacuum, or give rise to, let's say, reflection, refraction, dispersion, and how they can give rise to, they behave in different materials. And eventually we will also see how their this electrodynamics basically leads to special theory of relativity. So these some of the aspects we'll discuss in the next week. So when we come back for the next classes. Okay, any question?
Sir, please take the slide little down. Means upper portion I want to see.
Yes.
Okay.
So I will post whatever this I have done yesterday and today. So these lecture notes I will upload in the Google Classroom, so you can have a look. And these things are kind of, you can also see in your it is extensively done in the material that is shared with you. But if you go through that, so if you have any problem, miss any step or some confusion, so you can put up those questions also in Google Classroom. Okay, so the possibility is there. So you can post comment or anything that you want. So if you have any question, you can post it there, and I might try to address that even in the Google Classroom also.
Sir,
Yes.
when we change the means A dash is A dash sorry, A vector plus means magnetic potential. That
Not magnetic. So this is A prime, or A dash is equal to A plus a gradient of a scalar.
So A dash is basically magnetic potential, na, vector potential.
It is vector, yes.
So the magnetic vector potential, when we are changing, then at the end we are changing. We have to change the electric potential also.
Also, yes.
So means we will change the side dash in such a way that electric field will remain constant.
Electric field will remain invariant, not constant. So we should not say constant, but invariant. Yes.
Invariant. Then
Yes.
we have to means add that term or subtract that term. Means at the end equation. Means so that it will remain same. For that
So
we have
del
to
A prime by del T. So this is minus del A by del T minus, this is a minus term. So this is minus a gradient side plus Psi prime. Okay. So here we have to, yes. So because we have a positive term, so this psi prime has to be, okay. So you are saying this term should be negative, right? That is what
Yes, sir. Last equation, because we want to keep the electric field invariant. No?
invariant, yes. Yeah. So we have to have the scalar potential as psi minus del chi by del T. Yes. So this will cancel out. Yes.
Another thing, sir, magnetic circuit I was just going through. That I think we have not covered. Will you take means next class 5 to 10 minutes to just have a little?
So if you have any specific doubt, so maybe I can address that. So instead of going through the entire part, so because those are mainly about solving equations and problems. So you go, just tell me which specific part you want to discuss, so we can do that.
Okay, sir. I will cover that part. Then
Yes,
that will be better.
because if we cover everything, there is not enough time, as you can. So we
Yes.
already still have many more units to cover.
So basically, next class we will start electrodynamics.
So we have started electrodynamics, already started.
Okay.
So this is all electrodynamics that we are doing today. So we
Okay.
started with unifying electricity and magnetism in form of the electromagnetic, the Maxwell's equation, which is basically your starting point of electrodynamics. Okay. So this is a unification of electricity and magnetism. So that is the electromagnetic equation. And then when we talk about the electromagnetic wave equation in free space, in vacuum, so that is a form of electrodynamics. Okay. This is basically, already we are talking about changing electric field, changing magnetic field. So the next thing that we talked about is potential. So this is also part of, we are talking in terms of how the potentials will be getting affected due to this dynamics. Okay. And then, so already you can say the Maxwell's equation is the equations of electrodynamics. Okay. So that is why it is known as a classical electrodynamics. Okay. So once you are writing anything, a Maxwell's equation, so that is already means that you are dealing with electrodynamics.
Thank you,
Okay.
sir. Thank you.
Yeah. Okay, fine. Thank you. So then, so the next class on this electrodynamics will be on Monday. Okay, so electromagnetism and then continuation with the electrodynamics will be on Monday. So Monday I will take in the morning, as well as I think there was one like substitution we did with classical physics, if you remember. So Vivekananda sir, he
Yes,
took
sir.
one
Sir
class.
has taken classical
Yes.
mechanics 2 part.
Yes, yes. So I will take that class on Monday. So instead of, so I will take the class in the morning, as well as in the afternoon as well. Okay, fine.
Okay.
Thank you. Thank you.
Sir, sir, can you provide the notes that you are providing? Hello?
I will upload this lecture notes. Okay.
Thank you, sir.
Okay, thank you.